All right. It's great to be here. Um, yeah, I just gave this talk Thursday evening at the Radar conference, so I figured I wasn't going to change much in a couple of days. So, the point of this talk is to try to address this question that I have listed here, which may not make sense quite yet. Can immense CDR columns be used for tornado genesis prediction? So this is work I've been doing kind of off and on for a little while now, and that I'm kind of sick of and would like to finish. So much of my work over the past couple of years is I do climatologies using our 88D network of dual pole data. Since that upgrade to dual polarization capabilities was made in 2013. So whatever you might be interested in analyzing, there's theoretically 12 years worth of data of whatever that is. So I'm very interested in supercells and tornadoes, as you know. And so we've been looking at ways to use dual pole radar data to identify storms that may be more likely to produce tornadoes. So one thing that's come out of work over the past about 5 or 7 years is that there's this idea that the sizes of updrafts, and updrafts are just our organized area of rising air, and supercells, that their physical size or area is directly related to how strong a tornado can get. And so radars cannot directly see updrafts very easily anyway, but we can use some of the dual pole radar data to identify proxies for updrafts, and therefore proxies, we can identify proxies for updraft size using these data. And the way we do that is through something called the ZDR column. ZDR is one of the dual pole variables. It's an enhancement and differential radar reflectivity factor, which I won't get into, but let's just say this enhancement comes about because updrafts are lofting rain and small hail above the freezing level. So you have supercooled water that's being identified. And that's occurring where the updraft is. So we can use this signature as a proxy for the storm updraft. So I won't get into this too much, but the idea that formulated in a 2017 paper said, did all this theory that said, well, if you have a larger storm updraft, you're more likely to have a larger tornado, and that larger tornado is more likely to be more intense. And they ran some simulations in the center here to show that, when they ran computer simulations, there was a correlation between near ground rotation and the sizes of the updraft. So there was some evidence for it. So we came along and we were doing this, looking at large numbers of storms, and we said, well, we can try and test this idea by using ZDR columns and saying we can use the size of ZDR column as a proxy for the size of an updraft. So we decided to look at about 200 supercells, so a large sample, and see if the storms that had the bigger ZDR columns ended up producing stronger tornadoes. And they did. And the signal was quite strong, I think stronger than we expected. And you can see, so this we have a box and whisker plot here on the left, just showing the ZDR column areas for tornadoes rated EF1, EF2, EF3, and EF4 or 5. So increasing tornado intensity from left to right here. And then examples of the median for each tornado case here in the center. These are the ZDR column areas. So about 6 square kilometers for EF1. The median was about 20 for EF2, 33 for EF3, and 56 for EF4. All right, so we published that a couple of years ago. Great. Why am I talking about it now? So very important. This idea had nothing to do with tornado formation, just tornado intensity, peak tornado intensity. Nothing about tornado formation. However, we had non-tornadic supercell cases that we looked at. We had them, so we said, what the hell, let's analyze them. And what we found was somewhat surprising in that the non-tornadic cases consistently had no ZDR column at all, or ones that had very small areas. And so you see that here on the left. And so we published it, and we kind of equivocated a lot and said, well, we're not making this grand proclamation that we can use this to predict tornadoes, and we left it be. I came back to it a few years later and said, a different way, there's some overlap in these distributions, but a different way to look at it is that the non-tornadic cases really lacked consistently any of the really, really big CDR columns. In other words, the really big updrafts we weren't seeing in the non-tornadic cases. In fact, if we do this arbitrary cutoff of 40 square kilometers, we found 0 non-tornadic volumes out of 90 that had a ZDR column area that big. So for the purposes of study, let's call these ZDR columns that are greater than 40 square kilometers immense CDR columns, or presumed immense updrafts in supercells. And then we can say 0, we had 0 immense CDR columns in the non-tornadic cases. Now there's 2 problems with this idea that you can use an immense CDR column to predict a tornado. Number one, as I said, the original hypothesis motivation theoretical work did not link big updrafts to tornadoes. The second problem is sample size. We only looked at about 90 radar volumes of non-tornadic cases, which to me isn't quite enough. So goal here is very simple. Determine if immense CDR columns exist at all in non-tornadic supercells. If they didn't, of course, that would be a big deal, because that would mean every time you see one, a forecaster could say a tornado is going to form. All right. So how do I go about doing that? I like to take a climatological approach, as I already checked, because every supercell is different. They all have different structures, shapes, and orientations. Okay, so I'm asking this kind of what I would say is a hyperbolic question here: is do immense CDR columns even exist in non-tornadic supercells? So this is still ongoing, but I've gone from 90 to 556 non-tornadic volumes in 55 different supercells. Probably going to add like another 20 cases or so and get around 750 volumes. And so our hypothesis is that we would see them, because there were instances where I got close to 40, and 40 is arbitrary, but they would probably be rare based on our preliminary results. I'm not going to talk about this, but we designed our own algorithm to might want to guess, how do you determine CDR column area? Well, we wrote an algorithm to do it. It's called M-Trends. We just published a paper a few months ago talking about it. So here's reflectivity. Here's ZDR. This is the ZDR column in the circle here. And this is an artifact. So obviously, we'd like to. But the end result is that it spits out where the ZDR column is and not where the artifacts are, and automatically calculates the area. And this is 1 kilometer above the freezing level. So in this case had a ZDR column area of 25 square kilometers. All right, so that's how we do it. You can ask me more about how we define ZDR columns if you're interested in that. All right, so we just published that a few months ago. So these are the old results when we didn't have very many volumes. What do the new results look like? So in 556 volumes, we found 3 instances of immense CDR columns. These are violin plots, non-tornadic versus tornadic. And you can see where the non-tornadic cases are peaking, like 5 square kilometers, versus the tornadic, which have a wider distribution. So the point here is, yes, they do exist, but they're pretty rare. If you look at the distributions, the non-tornadic on the left, 10% have maybe ZDR column areas greater than 20 square kilometers, or that's the median for the tornadic cases. So there's really a very large difference in these distributions, which is, again, somewhat surprising to me. And even if we compare it to just the weakly tornadic cases, the non-tornadic are still much less likely to have an immense CDR column than even the weakly tornadic cases. So I said there were 3 examples of non-tornadic immense volumes. What do they look like? Well, they look like tornadic cases, actually. Here's one example. This one had a ZDR column of about 52 square kilometers, but it looks like a tornadic supercell, really. If you were a forecaster, you'd probably issue a warning for this. There's very strong low-level rotation. There's very well-defined supercell. The other 2 look like this as well. So I'm not claiming that these were actually tornadic cases. I'm just claiming that there seems to be this relationship between immense CDR columns and, at the very least, low-level rotation, in addition to seemingly tornado formation. Why? I said that the other big issue was there was no hypothesis. So why would there be a relationship between larger updrafts and tornadoes? Well, we do know what drives larger updrafts, greater mass flux, and that's driven by strong low-level storm relative flow, right? And so there's modeling results that show this very well. You increase storm relative winds, and your updraft, shown in black here, gets larger, right? And we've seen this in simulations. Well, so it's also, what we're also learning increasingly is that low-level storm relative winds discriminate between tornadic and non-tornadic cases. And so what we think here is that very large low-level storm relative flow gives us immense updrafts and also is an environment that is very supportive of tornadoes eventually forming. So I'll skip through this. So here's my summary. There's a lot of caveats here. So we definitely think that this is operationally useful at this point because the evidence is just becoming overwhelming. But there's a lot of caveats that I've listed here and that you can read through if you want. Big idea here is there's just a huge difference in whether you find one of these immense CDR columns, depending on how strong your tornado is and whether there's a tornado at all. EF4 is 72%, non-tornadic 0.5%, right? Just a huge difference. So that's what I've been working on.
I have a quick question. Yeah, right. Yeah, what environment is conducive to this immense updrafts?
So that's definitely, I have that listed here. So we definitely think that this is environmentally driven, that what's giving you the same thing as the large updrafts is also giving you a tornado. So that's what we're working on next, is directly, I have not done environmental analysis of immense versus non-immense, but that's, I think, the next step. And that's actually something that Jake Mulholland and I, who gave a talk here from Albany in the spring, that he and I are going to be proposing to work on with NSF. A combination of simulations and using environmental soundings to find out for sure what environments are supporting these. But last one, right now. No, sorry.
Michael, what does the role of the ground friction play in the convergence rates? In oceanography, we talk about bottom Ekman layers of cold core eddies that spiral in and then ascend through the ocean. So do tornadoes form over forests, for example? Was there just too much friction? Or
Yeah, there's a lot of ongoing work trying to relate what the what the surface looks like to tornado formation. Honestly, so I haven't really worked on that. The results are all over the map. It's kind of a mess right now because there's different ways that you could try to identify how you identify what the ground surface looks like. So some people take a statistical approach and find some signal, and then someone will look at in depth at one case and find no. What we do know is that friction. We do know that friction is more important than we had thought in the past. Yeah.
Okay.
Thank you.
Thank you, Michael.